Now let's see some examples of the fundamental theorem of calculus. We'll start with examples of part 2, which give us ways to evaluate definite integrals a lot quicker than we used to be able to. And we'll do the example that we did when we learned the Riemann sum definition of the integral. Integral from -1 to 3 of 2x minus 4 dx. So according to part 2 of the FTC, all you gotta do is find any antiderivative of this function right here. So any antiderivative will do. So x squared minus 4x. And we're going to evaluate this at 3 and then subtract the value at -1. This notation means first you plug 3 into it and you subtract the value that you get when you plug in -1. And there's no plus c for the antiderivative because we need any antiderivative. So we choose the one that has plus c equal to 0. And then you plug in 3. And then you do out the math. You get 9 minus 12 minus 1 plus 4. Which sure enough is the same answer we got when we did it with the Riemann sum, and also geometrically. And as you can see, if you did put a plus c in there, it would cancel out, because you'd have plus c here minus a plus c there. They'd cancel out. So that's the process. Find the antiderivative, plug in the top bound, minus when you plug in your lower bound. Let's do a few more examples. Let's do the integral from 0 to 1 of e to the 2x over e to the 2x plus 1. And try this one yourself too. So remember that all the methods we learned to find antiderivatives, use substitution and all those rules, they still apply here. And then just plug in your top bound minus when you plug in your bottom bound. So press pause and give this one a try, and then I'll do it when you're ready. Okay, now you've given that one a try. So this one's going to need u substitution, because it's not straightforward. So we have a fraction, a rational expression, and as is often the case, we let the bottom be u. Then we find du, and we solve that for dx. And in order for this to have worked, we need to have this e to the 2x cancel out, which it does. This e to the 2x and that e to the 2x cancel out. It leaves us with the integral, I'll do the bounds in a second, of 1/2 times 1 over u. Right, the 1/2 came from that 1/2, and then this is now u, so it's 1 over u, and then du. For the bounds. Now there's two options for the bounds. The first option is to do the same substitution. These are x values. That's x equals 0 and x equals 1. And this tells us how to turn x's into u's. So if we plug 0 into this, when x equals 0, u is e to the 0 plus 1. That's 1 plus 1, 2. When x is 1, that's e squared plus 1, which you can't simplify. And now we have an entirely new definite integral with all new variables, and there's no need to ever use x again. Once you change your bounds, there's no need to change back to u. Because now we can just do the antiderivative. There's no need for the absolute value around the u because everything here is positive. And then plug in your bounds. So 1/2 log e squared plus 1 minus 1/2 log 2. So that's the first method. When you're doing u substitution with definite integrals, you can change your bounds into also being in terms of u. The other technique, this by the way is what I almost always do. I almost always change my bounds. The other technique is when you change your variable, you pretty much ignore the bounds. And you just use this change variables to find the antiderivative. And then you plug back in the x expression for u, and then you use the original bounds. it gives the exact same answer. It's just two different paths, and sometimes the first way is easier, sometimes the second way is easier, so that it's all fine. But again, I usually change my bounds, but not always. Not always. Okay, let's do another example. Let's do a piecewise function. Let's let some function f of x be defined piecewise as cosine x for all x greater than or equal to 0, and as 2 minus x squared for x less than 0. And we want to find the integral from -1 to pi over 2. So the way this works, and feel free to press pause, do this out, and then press play to see the answer. But the way this works is there's no need for continuity for the FTC to work. As long as you don't have a vertical asymptote, you are good to go, at least for our techniques. And so what you want to do is just break up the bounds into the appropriate pieces. Like for all x that's negative, our function is 2 minus x squared. So this integral from -1 up to 0 is 2 minus x squared. And then plus, for all the positives, so from 0 until pi over 2, our function is cosine x. And this function is not continuous, that's not a problem. You don't need continuity for this to work. You just need to find the space between this curve and that axis. And so you do those out each on their own. So 2 minus x squared integrates to 2x minus 1/3 x cubed from -1 to 0. And then plus cosine x integrates to sine from 0 to pi over 2. And then you do each of those out. We get 0 minus -2 plus 1/3. And then plus sine pi over 2 minus sine of 0. And then simplify. So that's +2 plus 1. And there's our answer. So for piecewise functions, just break them up accordingly. Absolute value functions are also piecewise functions. Integral from 0 to 2 of absolute value x squared minus 1. Absolute value for me is almost always easier to see than it is to do algebraically. So let's look at this graph. So x squared minus 1, if there was no absolute value, looks like this. That's x squared minus 1. All the absolute value does is if the function is positive, the absolute value does nothing. If the function is negative, it flips it over into the positive realm, and if it's positive, it does nothing. So this graph in black, this is our function, and we want the integral from 0 until 2. So we want that space. And so we write this out. Now from 0 until 1, this is where the graph got flipped over. So this is the opposite of x squared minus 1. Because algebraically, when you flip something over, you change its sign from negative to positive, and changing your sign means multiplying by a negative. From 1 to 2, there was no change to our function, and so it stays x squared minus 1. So when you integrate an absolute value function, use the graph to figure out where it was flipped over, and then break it up into those pieces. And you finish it off. This, when you multiply that negative sign through, is 1 minus x squared, and so it integrates to x minus 1/3 x cubed from 0 to 1, plus 1/3 x cubed minus x from 1 to 2, and you plug that in and you get your answer. I guess I'll do it all the way out. From over here, we have 2/3, and you do out all that math. And over here, it's going to be a little bit trickier. we have 8/3 minus 2, which is 2/3, minus 1/3 minus 1, which is plus 2/3. We got 2/3 all over the place. The answer is 2? That does not seem right. Just check it out. But this, at this step, it's for sure correct. And then do out your own math and figure it out. Maybe I'll come back to that one and make sure it's right. But probably not. I'll probably just kind of ignore it. Okay. Give this one a try on your own. The integral from 0 to 3 of x squared square root of x cubed plus 9. And that's x squared, x cubed plus 9 from 0 to 3. So press pause, do the workout, and then I'll show the answer in a second. Okay, so we have u substitution here. U is x cubed plus 9. Du gives us 3x squared dx. When we solve for dx, we get 1 over 3x squared du. The x squareds cancel out, which we want. We change our bounds, because that's what I like to do, and we get 9 to 36. You get that by plugging u into this, and by plugging, by plugging 0 into this, and by plugging 3 into this. And our integral is now 1/3 u to the 1/2. Which integrates to, we add 1 to the exponent, so it's u to the 3/2. Divide by 3/2, you get 2/9. Since I changed my bounds, there's no need to plug back in, and I do my math to this. 2/9, 36 to the 3/2, minus 9 to the 3/2. 36 to the 3/2. We'll do the half part first, because 36 to the 3/2 is just 36 to the 1/2 cubed. 36 to the 1/2 is 6. 6 cubed is 216. 9 to the 1/2 is 3. 3 cubed is 27. And then we get our answer. When you subtract, this gives you, see, 216 minus 27 is 189. Oops. $189 is actually a multiple of 9. It goes in there 21 times. So I guess it's 42. That's a surprising answer. It's worthwhile to check that also. There's a chance, by the way, that I'm messing up some of the arithmetic. If that happens, just use like Wolfram Alpha. Wolfram Alpha is a great place. You can put this integral right into Wolfram Alpha. You just say, like in words, integrate the function, and then from 0 to 3. And Wolfram Alpha will find the answer to you. Wolfram Alpha is a great way to check your work. So if I was doing this for my work, I would check these answers in Wolfram Alpha. Okay. So now we'll move on to examples of part 1 of the fundamental theorem of calculus.